Is the screen audio,
Yes,
audible and the screen visible now?
yes, sir. Yes, sir. It is visible.
So I think we had many lectures in last 3 days. Today I would like to discuss more about the uh, cloud load scheduling and resource management and run some basic codes on one of the systems in the CDAC Pune. Our focus today is what are the load scheduling and job management softwares available in the cloud and what have been considered as open source software and integrated with the cloud. These things we'll discuss. Before that, we'll give some overview for 30 to 45 minutes. After that, we log in onto the systems and then try our best to demonstrate some codes actually. And you will be getting some understanding about the various applications and programming environment, what we need to focus in the cloud computing. We also discuss about the security also. Okay. So now the Azure cloud, they started called Cycle Cloud. Slum. Slum is the load scheduling and job management software, which has been integrated with the Cycle code. And these are the research activity going in the Azure Microsoft. And then we'll get some exposure about these things. Let us see. As we discussed earlier, not only by me, but many of the speakers, the entire cloud computing is depends upon the parallel distributed computing technologies. And most of the applications are classified as high performance computing user, high throughput users. High performance computing is the raw speed where you do the computation, where high throughput is the more number of jobs you process simultaneously. Both are now in terms of large clusters. Maybe if you see high performance computing systems, which are there in top 500 benchmarks, they have more than a few million cores with the GPUs. And high throughput computing, where the Google, Amazon, Facebook, many of them are having this high throughput computing, cloud computing setup. They also have more than a million cores with a large number of GPUs. So if you really see first we go through the high performance computing and high throughput computing, how the programming environment is there, how the load scheduling job management softwares are there, what is the job schedule, load scheduling and job resource management software, that is Slum, how it has been integrated, that we'll discuss. What you really see is that from last 20 to 30 years, initially you have the shared memory systems, SMPs. Now it has become the non-uniform memory system called NOMA based system. Then we have moved on to the clusters, where the set of desktop systems are connected with Ethernet network, where they have reasonably high latency and low bandwidth. Later, they have come down to the MPPs, massively parallel processors, where the processors are tightly coupled with low latency and high bandwidth. The next one is distributed computing system. All these things have been connected by different kind of networks. One is the peer-to-peer computing system, peer-to-peer networks. The second one is InfiniBand networks. Third one is gigabit networks. That's one side. But last 15 years, every system is having GPU accelerators as well as FPGA accelerators. These FPGA accelerators are sitting in the PCIe 16X slot, true with the GPU accelerators also. And the GPUs are much powerful than the CPUs because most of the ALUs are directly addressed to the memory in GPU. GPU has high memory bandwidth. And that way, GPUs are very, very powerful in terms of floating point computations. Today, almost all the AI applications with 8-bit, 16-bit, and 32-bit, 64-bit, they run on the GPUs actually. On the other side, you see shared address place platform where the more number of cores on a given system, which we call as a head node of a large cluster, they have more number of cores and more memory. That means on the head node, you can able to load the large amount of data, and then you can distribute data onto the every node and do the parallelization. That is how the evaluation has come in the high-performance computing. This is how the typical cluster. You have the standard compute nodes and you have the InfiniBand or the Ethernet or the other kind of community networks. And the single system image is the most important, where the single system image at the application layer, single system image where the CPU, GPU you can see, unified memory. And today the programming paradigms are basically NVIDIA GPU, CUDA programming. OpenCL runs on all the devices, including AMD, Intel, and Hadoop MapReduce and Spark. And PyTorch is GPU enabled. And now PyTorch is also completely MP enabled. That means PyTorch runs on distributed training directly. All the programming paradigms, if you really see, some come under the high-performance computing, some come under the high-throughput computing. And how they are basically provided, that is also we need to understand. So that means the cloud can be considered as the cloud will have more number of systems. They are integrated. When they have more number of systems, some system may be SMPs, some system may be non-uniform memory kind of systems. With the internet, maybe InfiniBand, gigabit or peer-to-peer networks. Some of the programming APIs where the cloud, which are distributed in nature, they are using grid computing since a long time. That means if you really see, as you increase the more number of processors, you also see the size of the machine and you also see the scalability also. And if you really see cloud here, you can have multiple OS images through the virtualization. That is how the cloud can be thought of as a combination of all the systems actually. Then how we can address the load scheduling and job management software, that is also another important issue. That means if you really see, go back, you have centralized computing, parallel computing, and distributed computing, then the cloud computing also there. In place of, in between the distributed computing and cloud computing, we have the utility computing, we have the grid computing, and with all the things, today the cloud computing is much more matured in terms of handling complex programming environment as well as the load scheduling and job management software. And we also, CDAC India, we have the grid computing project in the year 2002, 2006. There we have the multiple supercomputing site. They are connected by the single private network, which we call as the Garuda grid, which is powered by the National Knowledge Network, NKN. That means if you have a cluster of systems, you can talk about gigabit Ethernet. You can talk about peer-to-peer network. You can talk about the systems which are geographically scattered using a NKN network. All these things, networking also very, very important besides the load scheduling and job management software. Now, if you put all things together, you have the one-way web services, we have centralized computing, distributed computing, parallel computing, peer-to-peer computing, grid computing, all these things are technology converged actually. Many of these things have been extensively used in the business computing. Yes, I'm audible now.
Yes, sir, you are audible.
So 80 to 90% of the business applications require all these kind of computing concepts actually. Now let us see. That means you have high-performance computing system and you have some load scheduling and job management software where you run your jobs, where each HPC system having 100,000, 10,000 nodes, and they have different kind of networks. Other side, you have HPC systems, high throughput computing, and cluster of MPs, cluster of MPPs, and you have the internet clouds, virtualization. All these things are coming under the single umbrella. How do you really address it? In fact, here, the left side, it's a high throughput computer, high throughput systems, which are written HPC systems. Some correction we need to do. So this is how the thing. Now let us see on other side, when both the systems, high throughput computing, 1,000 systems are joined together. High performance computing also another 1,000 systems are joined together, big, what we call as a cluster. How the file systems are there, how they have been designed, that is also important issue. One is high throughput computing, where it has a standard Hadoop MapReduce with HDFS or the Spark with HDFS. That is how it has been designed. And if you see the features of the HDFS and features of the Lustre is a file system for the high performance computing. HDFS is another file system for the high throughput computing. If you really see all the things about the, many of them discussed yesterday about the name node, data node, as well as the job tracker, task tracker, master slave architecture of the Hadoop MapReduce, and many of them discuss about the replica of the Hadoop MapReduce system with HDFS, how it works on the overall write once, read many times on one side. Other side, we have the Lustre also, we have the, it's a fully POSIX compliance where the file system is partitioned blockwise and then processing data. And then this is how the, both of them are using for the different class of applications. And both HDFS and Hadoop MapReduce as well as Spark, they meant for big data analytics where the large amount of data is processed, where the each data is partitioned as chunks, each chunk is of 64 MB, 128 MB. Whereas if you see Lustre file system, they have the different kind of programming paradigm called message passing interface MPI, or the much earlier PVM kind of parallel virtual machine. And that is how the programming paradigms have been developed for last 20 years actually. So when you come to the cloud server system, whether in the cloud computing, you may have the HPC system or high throughput HTC system, HTC. That means what the cloud computing service provider, basically cloud service provider CSP, looks for scale out. That is, add more number of system processors on the fly. And elasticity, that means your network and storage, everything should be handle the scale in and scale out kind of system so that your performance will be achieved. High availability. So these three factors are basically in the cloud computing, we need to address it. That means basically what is important is whether you have high performance computing with some programming paradigm, how the load scheduling and job management software is addressed, high throughput computing, Hadoop MapReduce or Spark, how the load scheduling and job management software is addressed is one of the issues. So what are the major issues when we do the load scheduling and job management software? Only many of them are discussed about these things in the last 3 lectures. I give a little bit overview. One is performance. Second, tier 2 is the scaling up. These two we need to address it. And third one is availability. Fourth one is the replication. So these all four very important from the high throughput computing. Whereas from high performance computing, replication may not be completely there. Whereas fault tolerance may be there in the high throughput computing, fault tolerance may not be there in the high performance computing. Fault tolerance means the large cluster of 1,000, 10,000 million nodes which are joined by InfiniBand kind of network. When the job is processed, if the one node gets not responded, then the fault tolerance is fully exists or not. These are the questions in high performance computing. Whereas in high throughput computing, these have been addressed actually. So now let us see. That means when it comes to the load scheduling and job management software, I only see I have parallel and distributed computing programming paradigms. My job runs with Hadoop or iterative MapReduce, Hadoop distributed file system with different kind of storage in the Hadoop. And I have the various features which Amazon cloud provides and Microsoft Azure provides. All the things are there. And I have high throughput computing and high performance computing systems are there. And programming point of view, I have the Hadoop MapReduce and Google has the Google file system and Google is a MapReduce. And there is a storage and big table and then big hive, many are there actually. Now, software components also there. And you have the cloud administrators where the jobs can be processed on a high performance computing cluster or high throughput computing cluster. That is also very important. Now let us go to the high performance computing. How the high performance computing is there and how they're basically worked out in the last 10-15 years, that we'll see actually. One is they call message passing paradigm, message passing programming paradigm, MPA. MPA is used to connect the large number of systems, and once they connect it, they run processes on their cluster. And for user, it is a single system available in the background. Many systems are integrated with different kind of network. Here the latency and bandwidth is most important. And number of processes you run, that means every process is has a unique rank, a non-negative integer. If you run 100 processes, then the rank will be vary from 0 to p-1. The most important is to whom data is sent, what is sent, how does the receiver identify it. Here, good analogy is post office is a good analogy. How the post office works in many countries, same thing MPA also works. MPA is a library which you can connect to the more number of systems. Now, if you really see here, the left side, they can see. The left side you see clusters actually, where each node may have the 8 or 16 cores, or each node may have the GPUs. Today, CPU and GPU unified memory address is there. NVIDIA also has their own CPU and own GPU. AMD has their own CPU and GPU. And then Intel also has their own CPU, GPU, and FPGAs. And these are all running on the cloud. And right side, you see how the message goes from one processes to other processes. Processes 0 running on a system 0. Processes 1 running on a system 1. And this processes 0, processes 1, processes 2, they are running. It is all managed by load scheduling and job management software. The load scheduling and job management software is basically one of the most popular today in high performance computing is SRUM. This SRUM is basically now integrated with the cloud also. In future, today many cloud service providers, many HPC service providers, they have their own schedulers, own load scheduling and job management software. But SLUM is going to be more standard and it is open source. It is integrated with the cloud also, that we will be discussing, and we'll run some programs also. What you see right side is the typical how the letter has been posted by sender, how the letter is carried from the mailbox to the post office, how the letter will be delivered to the another remote post office by carrier, and all these things are nothing but high layers, higher layers, middle layers, and lower layers. At every layer, what are the important communication, computation, abstract level of message passing, everything is very, very important. These all come under the, when we integrate high layers, middle layer, lower layer, the cluster file system or parallel file system is going to come. Whereas for the high throughput computing, you have the Hadoop distributed file system will come and MapReduce library will be coming actually. So we need to understand these concepts very well. That means in the large high performance computing clusters, you have the interconnection network, maybe InfiniBand, gigabit, or the fast Ethernet, and you have the load management and job scheduling management that is there actually. Here, MPA running on a single system in a shared mode it runs, and MPA across the nodes, it comes under the explicit message passing. So this is how the MPA programs really run. Simple hello world program where process P0 means every process is want to send a message to process with rank 0. That means P1 sends to P0, P2 sends to P0, then P0 receives from P1 and P0 receives from P2. That means process 1 is sending to process 0, and then you have the network interface card, switch, and your routing algorithm, receiver network interface, receiver user space, and the message will reach. And now if you really see actual applications, people here are using 2 processes, but in real life they are using 1 lakh, 2 lakh, 4 lakh processes. And all this come under the large scale scientific applications, and they are available under the top 500 supercomputing benchmarks. All the top 500 supercomputing benchmarks, they have 1,000, 1 lakh, 2 lakh systems. Each system is having 4 to 8 GPUs, and then GPU compute capabilities are more than 4 to 8 times powerful than the CPU, and they run the programs actually. And as I discussed about how the communication goes, application, presentation, this is how the standard 7 layer, this is how the message goes also. How at every layer, how it interaction happens, and how the message goes from source node to the destination node, sender to receiver, all these things, how the MPA message passing library MPA works, that is also very, very important actually. So this is how the MPA message passing interface library you can combine with the C programming, C++, as well as the Python also you can combine with MPA, and MPA with GPU programming also we can combine and run the programs. So MPA has got abstract device interface, and below the abstract interface device there is a fast messages are there. Then the network will be there. Then routing algorithm will be there. Then message will travel. That is how it happens actually. That means for one node to many nodes, we need to understand what is the time taken for the point to point, what is the time taken for the broadcast, what is the time taken for the collective. All things we have to understand in the question of MPA actually. This will only determine for any application running on HPC cluster on the cloud, it only determine how much is the cost of communication, how much is the cost of computation. That's very, very important. That means if you really see the cost of communication and cost of computation is going to drive the performance of application on HPC under the cloud, then what we need to understand is how many layers are there, and how the device layer, how the communication system is designed. All things are also important in the case of MPA. That's what the abstract level of implementation everything. Now, when we put the GPU on the PCIe 16X slot, then CPU interacting with the GPU, many GPUs are there, means GPU to GPU communication. In the case of NVIDIA using NVLink, all these things boil down to the cost of communication in the software stack. And the cost of computation is how much computation you do on the CPU, GPU, that is also there. So total cost of computation and cost of communication involving all the nodes in HPC cluster drive the performance. That means you can book 8 nodes, 16 nodes, 32 nodes, of HPC system under the cloud. Nodes means a compute node, and every node may have the GPUs actually. So that is how the things actually. Now, if you see from the cloud computing perspective, high performance computing, MPA based clusters are there. Beginning in the cloud, they have only Hadoop. If you see from cloud perspective, you have the high throughput computing that is come under the Hadoop MapReduce, HDFS. Similarly, Google File System and Google MapReduce. That's how. How they evolved in the large clusters and how we are able to provide the load scheduling and job management is important. That means in the Hadoop clusters, let us see background actually. Hadoop on demand, that is another way, one way to start it in the beginning. Then they have the shared compute clusters. After they have the Yarn cluster. Yarn is the load scheduling and job management software which is running on the Hadoop clusters actually. Now that means many of the Hadoop MapReduce and Hadoop distributed file system Yarn, these are all open source software. Similarly, from the high performance computing side, you have the entire MPA library is open source library, open source, and Slum is also another open source. So that is how they have moved actually. Now both things come under the cloud exist, that is called cloud load scheduling and job management software, that is called Cyclic Cloud, which we'll discuss also. Now, what are the requirements from the Hadoop side? One is scalability, and second one is serviceability, multi-tenancy, locality awareness, high cluster utilization, secure and audible operation, reliability, programming model, and compatibility. Same requirements come under the high performance computing also that we will discuss. One is scalability, cost of computation, cost of communication, how the services, how can I run my job on 8 nodes, 16 nodes, 32 nodes, locality awareness, how my internet, my InfiniBand kind of connectivity is really deployed at the programming level, point-to-point communication, collective communication, computation. That means if N is a message size, P is a process is, order of NP for broadcasting message from one process is to 1,000 processes. When I say one process is to 1,000 processes, all 1,000 processes are spread on different compute node that has been managed by the load scheduling and job management software with MPA actually. And security is the security authentication authorization. So many are there in the high performance computing cluster side and high throughput computing cluster side. Both are now merging. Both are actually going to provide a common load scheduling and resource management software under the cloud to handle both the things. The advantage here is that the cloud service provider can able to automatically find out whether the job is high throughput computing using Hadoop MapReduce or the job is high performance computing using MPI, then he can automatically find out the compute nodes on the fly and then able to launch the job actually. So these are the way. That means we should understand how the load scheduling and job management software runs on the high throughput computing. That is what the Hadoop MapReduce or the Google kind of systems, or the how it runs on high performance with the cluster of compute nodes with the GPUs using InfiniBand or using gigabit kind of network, or the Intel Dragonfly kind of network. So now if you see all the things, how the load scheduling and job management software has been designed for the high throughput with the Hadoop side is called, they call Yarn. Yarn, these are the things which are basically scalability, serviceability. Whenever you talk about serviceability, if you really see serviceability, the cluster software has been changing in last 15 years. Last 3 years, the cluster software is gone the only PyTorch. Now PyTorch, TensorFlow with NVIDIA GPU programming, and now with the MPA, it runs also. That means the earlier we have Torch, then integrate with Python, PyTorch, then PyTorch integrated with the GPU one side. Other side you see MPA with Python, and MPA with the GPU, and all things have been also becoming many things actually. Okay. So now let us see what other things actually. When it comes to the cloud computing and today's era, we talk about the data processing, security, authentication, authorization, and we also talk about the availability of the systems and reliability of the system because of we have the complete heterogeneous programming. So this is how the yarn actually. That means if you really see from last 15 years, how the yarn is basically gone is that if you see the era of ADA clusters, ADA of Hadoop demand, similarly, if you see high-performance computing clusters, 20 years ago, we did not have a complete single system image at the software stack, single system image at the complete user level. Now, today we have the single system image. That means users can seamlessly run jobs on high-performance computing cluster. Similarly, users can run jobs on the high-throughput computing cluster also. So both can be coexist today. So now that means what we require in the yarn is a resource manager, application master, resource model, resource requires, container specification. Parallelly, we also have in the entire Hadoop is a name node, data node, job tracker, task tracker, a pig, and other HBase. Everything is ecosystem is there. Complete ecosystem. Now we are integrating all these things. So in the my next lecture, I talk about the Hadoop Python codes running, Hadoop Spark codes running, and I also talk about the databases in my next lecture. Today's lecture, I only give more on the high performance computing. I will try my best to run some jobs on my systems here with the Slum also. So here, Apache Hadoop MapReduce, you have the task tracker, and then you have the job tracker, and you have the client is there, and job submission. This is how the at higher level way of looking into the yarn resource scheduler actually. If you really see today, and you have the, now we are introducing the complete virtualization, and we have the container, and I also discuss about the Docker container, serverless computing. All things have been also brought onto the node manager and application manager, how this also can be looked into the overall yarn actually. Now today, you can have the yarn file system if you see POSIX compliant, not fully POSIX compliant, whereas in the high performance computing, most of the file system are POSIX compliant, what we call as a parallel file system or general file system. Now, MPA reduce, MapReduce, and MPA both can be integrated also. Both can be integrated, and the node manager can really run both the things actually. That means the central resource manager in the Hadoop MapReduce, it automatically handles non-MapReduce jobs, that is MPA jobs, as well as MapReduce jobs, that is MapReduce jobs actually. All these things are basically done very well by the scheduler and application manager. But if you really see, that means every service provider have their own schedulers as well as the own load scheduling and job management software running. But today, every high-performance computing system runs only runs the Slum actually. Now, the Slum has been integrated with the Hadoop MapReduce, and efforts are going on also. Let us see. So Hadoop, how the Hadoop yarn has been designed is these are Hadoop cluster. These are the Hadoop ring. They call Hadoop on-demand architecture. They have the resource management layer. This is how the Hadoop. You have the shared HDFS. And I'm not going more details about the MapReduce or the task tracker or job tracker or the name node, data node, which you must have got exposed. I'm moving this one. Now we'll talk about the Slum with the cycle cloud, and then we'll get back to some of the access systems access everything. Okay, let us see. Slum Azure Cycle Cloud. Background, what is the background actually? Slum means simple Linux utility for resource management. It's an open source workload manager, popular in many of the supercomputing this thing. I can close this one now. Resource management. Now, Azure Cycle Cloud is also a platform for providing, managing, and orchestrating HPC clusters. But Azure Cycle Cloud, it also has complete security and different kind of services actually. Okay. Now, since Slum is the open source software, a lot of motivation has come in integration with the Slum and Cycle Cloud actually. That means maybe in down the line future, the Scrum automatically runs on high throughput computing systems. Scrum is already running on HPC systems. Then all your hybrid workflows, resource management can be handled by this one actually. So presently it is integrated with the Scrum, but now they are integrating with other load scheduling, job management software also. Okay. So what is important is that it combines cloud native high performance computing and it's efficient in scaling because Slum is already popular in high performance computing which runs on 1 million, 2 million compute node systems. Similarly, Cycle Cloud runs on high throughput computing system. So that means actually high throughput computing and high performance computing both are basically addressed through the Azure's orchestration platform for HPC. That is nothing but integration of Slum and Cycle Cloud actually. Okay. That means what? You can access the HPC resources very, nowadays HPC resources are very much essential for the all the distributed training in deep learning and distributed inference in the AI. That means all the distributed training and distributed inference, we do distributed training, we have done with 64-bit, 32-bit. Now almost all the vendors, they provide bfloat 16-bit computation, 8-bit and 4-bit, including Google TPU, NVIDIA GPU, AMD GPUs, and Intel GPU, FPGA, CPU with SQL programming. All these things basically you have, what is required is that scheduler, a master node, and execute worker node, shared storage, networking. And then now how the configuration via cluster templates in Node.js has been integrated. And you have the CPU partitioning, you have the GPU partitioning, you have the combination of CPU, GPU, so that many partitions can be provided to the user either through HPC work or through the high throughput computing. But now if you have a large system with more than 1,000 cores, then you can also use this high throughput computing, high performance computing, where you do socket level partitioning, maybe 8 socket and 1 partition, 16 sockets and 1 partition. That's how the industry is moving actually. So now, what are the issues with Slum cluster management job scheduling software? One is user and admin workflows, job submission. The job submission is basically they have the SBatch, SRN, and job monitoring, and auto scaling, that is elastic compute node management, that is scaling policies based on job load and cost impact. Based on the job load, you can allocate more number of processes, less number of processes. And how do you really monitor the entire cluster health and performance? How the job accounting and troubleshooting has been done. All these things which are existing in the high performance computing clusters, now they have bought in a single umbrella. That's where the Scrum and then Azure Cloud is basically going to drive actually. So now other thing is when you use the Azure side, you need to talk about authentication. You need to talk about authorization, LDAP, that is Azure Active. One is services, LDAP protocol, and Azure services, how they can be integrated, how the secure network and how the node isolation, single sign-up, SSH access, and quota enforcement, cluster access. Many of these things may come from the high throughput computing Azure side. Some come from the high performance computing. Both are integrated today actually. Okay. Now let us see. When you talk about Azure Cycle Cloud, what's happening in last 5 years about the load scheduling and job management software? There are many schedulers are there. One is Scrum is the more popular, and PBS Pro is PBS Pro and Contour. And LSF is another load scheduling software, and IBM has their own load scheduling software, LSF. And Grid Engine, we talked about the grid computing, where the large number of distributed systems are integrated together, which are geographically catered. HT Contour, Cycle Cloud. That means Cycle Cloud today, the work has been done for the integration of Slum and Azure. Now, automatically you can plug in many of the load scheduling and job management software also. Okay. Now, in the case of Azure, you have the more virtual machines. You need to manage it, and you need to have a less number of virtual machines or more number of virtual machines based on your flexibility of the compute sources, so that you can meet the dynamic workload. That means you need to manage the compute resources also. Auto scale means cluster size can be increased or decreased. But now, if you see all these for earlier, there were no GPUs. Now GPUs also come into the picture. Earlier, less number of threads used to run on the every node because of 64-bit double precision. Today, you run a few million threads on every system with multiple GPU, because you compute 8-bit, 16-bit also actually. So that means you need a different kind of integrated framework to handle HPC workload and high throughput workload. You also require different kind of visualization tools, and you also require plug-in play of the many schedulers which are required in the Azure cyclic cloud capabilities actually. So now there is a first we will take some few minutes. After a few seconds, we'll go to the demonstration and we talk about the more about the Slum, and then we talk about the more Slum commands and everything also. One of the important policy is that whether the job is run on high performance computing or high throughput computing, centralized authentication and management is a fundamental issue. Centralizing user authentication and authorization from security perspective is very, very important. How do you really important actually? And when you integrate many of the schedulers from outside, then what are the protocols and what are the services which are there, active services, protocols and services? How do you really integrate with the user access, and how do you enforce security policies? These are also very, very important actually. So that means what? We need to see the user's home directories and SSH access. We need to configure centrally, and we need to integrate with the LDAP protocol and then AD services with the client server systems very carefully. All these things are very, very important when it comes to the Azure Cyclic Cloud also. I just skipped some portions. Now I'll go to the now, if you really see how the LDAP and Active Directory, LDAP protocols and Active Directory services, some of them are extensively used on the high performance computing, some of them are used in the high throughput computing, and they come under the integration with the Microsoft or the Azure integration, or you have the decide clusters and then networks, everything. All things we need to put together in a single framework under the Azure Cyclic Cloud actually. Okay. So we just quickly go through the some of the codes which we run now. Then we come back to the how the integration has been done. Before we go to the programs, first we should understand integration of Azure Cyclic Cloud is done with the Weka data platform system. The Weka data platform system and Azure Cyclic Cloud have been integrated actually. Okay, that means what? Basically, this particular Weka data platform delivers from workloads from high performance computing perspective. That is data intensive workload, and high throughput computing workloads also handled by the Azure cloud and then integrated everything actually. So this integration of both the things are very, very important. That means both integrations have been done using what they really use. Let us see actually. In the Weka, they use the Slum as a load scheduling and job management software. It is designed to handle low latency, high throughput workloads making it suitable for the high performance domain, as well as AI analytics, as well as machine learning also. Whereas Azure Cycle Cloud, management of HPC clusters, high throughput clusters, and providing dynamic auto scaling, both will do. So both are basically now integrated. They are available now, and they use a lot of open source software actually. Now, what is Azure Cycle Cloud? Provision of infrastructure. Quickly set up the compute and storage sources required for HPC workload. That means you may ask 1,000 processes, 10,000 processes. You may require few terabytes of storage or few petabytes of storage. You may require GPUs. All these things, how do you set up on the fly required for HPC workload actually? Then how do you integrate with the schedules like Slum and Grid Engine or HPC pack is also very, very important. So what we do, we'll talk about some of the applications, then we'll come back to this one. First, we give some idea about the Slum also, then we'll compile and execute some programs in the high-performance computing system using Slum, and then let us see the idea also. Simple Linux utility for resource management. Am I audible? I hope going well.
Yes, sir, you are audible.
So what we do after 5-10 minutes, we will demonstrate some of the codes also, and we also see how the Slum works on HPC systems actually. Okay. So users efficiently run large-scale parallel and distributed applications across clusters of compute nodes. So that is how do we really run. Similarly, high throughput computing workloads also you can run parallelly also. Let us see. So what are the Slum features? Job scheduling, resource management, and fault tolerance, as well as power management. So power management means you need to provide the compute nodes, and you need to see what is the power consumption when you do compute, when you move the data. That also we need to take care of in the load scheduling only. And fault tolerance is another one which has come through the high throughput computing. High throughput computing, Hadoop distributed file system, fault tolerance, and replica, that is another positive point. In the high performance computing, fast computing, low latency, high bandwidth kind of communication, and performance driven, that is another part of HPC. So both are integrate. You have to choose the right kind of application which requires both, or it requires either one or two actually. Now today you have the computer resources, the CPUs, GPUs, and memory. Maybe in the down the line through 2 to 3 years, we have the CPU, GPU on a single chip, and everything is going to be on the chiplet network, CPU, GPU, everything on the chiplets. We have multiple chiplets will be there, and each chiplet will have more than 68 core, 128 core, then you get the better performance actually. So these are the Slum key features. So now Slum is available. Slum is available in most of the top 500 supercomputers because its scalability and flexibility. Now, in the Azure Cycle Cloud, Slum is only currently integrated. It's an open source actually. And additional softwares, additional PBS Pro, LSF, they are also going to integrate in the Azure Cycle Cloud so that it supports the many of the third-party load scheduling and job management software. But when third-party load scheduling and job management software is integrated, we need to talk about LDAP protocols, we need to talk about the access directories, many things we have to see. Because whenever we plug the third-party load management and job scheduling software, then we need to see from the security and policies and compliance and everything also. So what is the architecture which we are, today available in the cloud is, cloud demonstrates how Azure Cyclic Cloud integrates with the Weka data platform and Slum deliver actually. So what it delivers, high performance computing solution for the many applications and high throughput computing solutions for the many applications also. That means high throughput computing, Hadoop MapReduce, HDFS, Spark, Hadoop and Spark. Now both are moved on to Hadoop MapReduce Python and Hadoop and Spark. And MPI side, MPI is high throughput, high performance computing, that's moved on to MPI Python. and GPU programming, PyCoda, Python Coda. So a lot of things have been moving very fast. All things we need to provide on a single umbrella. That is what the Azure Cycle Cloud actually. So today in the lab session we run the high performance computing codes. We use the Slum. That means in down the line 2 to 3 years, Slum is the one which takes care of everything, which takes care of authentication, authorization, availability, serviceability, replication, everything it takes care actually. Okay. So now what are the key steps in this cycle cloud actually? One is automatic vacuum mounting. That means when it comes to Hadoop MapReduce, first is this one that is not come. Job submission. User submit HPC job through scheduler specifying a number of Azure virtual clouds to deploy. That means user can specify how many VMs are required, it will automatically deploy actually. VMs can be maybe required for the HPC application or high throughput computing application. Or if you want, when you have a large system, I can do socket level partitioning and make a one partition to one user, other partition to another user. I can launch many VMs also. So now Azure Cloud also provides virtual machine scale set. That means more resources available on the virtual machines as per your demand, workload demand. That also we can integrate now actually. So that means what? Whether my job is HPC or high throughput computing, both can really coexist and both can really define the resources required. It dynamically configures all the things actually. Automatic vacuum mounting. That means how many compute nodes are there and how the storage cluster is built and how performance storage means you have cluster attached to storage or you have network attached to storage or you have direct storage or HDFS storage on every node. All things now integrated as a single framework to provide actually. Okay. Job execution also there. That means you have the GPUs, as well as you have the CPUs, and you also have the NVMEs. That is what the storage access, storage, scalability, and cost efficiency, flash area of SSDs. All these things can be now integrated for the job execution. That means you have the a scheduler where you can provide, I need this many VMs. I need this much size of flash array with this intermediate memory. I need this much amount of storage. All these things we can really plug with the Slum scheduler actually. So data persistence after the job completion, the data which is there basically, how do you really store the data? How do you do long archiving? That is also available actually. Okay, that means what? VACA HPC, VACA storage capabilities and framework for HPC, HTC, high performance computing using Scrum scheduler, everything is integrated into Cycle Cloud actually. Okay. So now this is how the HPC nodes will be there. High throughput. In the high throughput nodes, you may have 512 core single address space system or 1000 core single address space system. You have the Slum scheduler is there, and you have the Cycle Cloud virtual machines are there, and you have the NVMe tier, you have the flash area of SSD, and you have the storage, and all things can be brought under the single umbrella. That is how the Azure Cyclic Cloud with the Vega data platform is going to be more popular. Now you can plug the third-party schedulers and third-party resource managers. Then it automatically takes care of the LDAP as well as the directories and then do the thing actually. So now what we do is that how we can really provide this one, and we'll take some 1 or 2 minutes break here and then we'll go back to the lab sessions actually. I'm taking break. Am I audible now?
Yes, sir. Yes, sir. I will write in chat box.
Just 1 or 2 minutes. I will log in and then slide. I'm audible now?
Yes, sir, you are audible and the screen is visible.
Thank you very much. See, what we are seeing is uh, we have logged on to the one head node of a cluster where the Slum is running actually. Okay. So first we'll see what the system is. We put one command called top. Top is a Linux utility tool. When we say it say what's running on the system, everything, memory available, everything. When I press some numbers, it says many CPUs are there in the system. Okay. So many CPUs are there. You are able to see CPU 0, CPU 1, CPU 2. Visible now?
Yes,
Visible
sir.
now?
Yes, sir, it is visible.
CPU 0, CPU 1. So what we have taken one Slum cluster for this work, and we are able to see how many CPUs are there. We run one simple program. That's what how many logical CPUs there are. Physically, there are 48 CPUs are there. We are disabled the hyperthreading. That's why it shows 48. If hyperthreading is enabled, then it will become 96 actually. So this is what the thing. Then what we do, we need to see what are the programming paradigms which are there, what user can use. That's what we do on the cluster. In the case of Slum, automatically they are available. User has to automatically compiles, executes, everything goes parallelly actually. Okay. So let us see. The first thing is that we'll go to the one URL directory. Let me just go to the simple program where normally there are two things. One is in all the HPC applications, you have single binary runs on all the system. That is called single program multiple data. Whereas on the some situations where multiple binaries, there is multi-program, multiple data, MPMD model. Okay. Now we are running high performance computing. Next day, or the maybe next session, I will run the high throughput also. High performance computing means MPA is the library, MPA library and C program, MPA C++, MPA Python, and MPA Java, they are integrated. MPA is a library which does the communication exactly similar to the post office analogy, which we discussed also. So what we do, we have to see what is the MPA there or not. It's called which MPA CC. So MPA CC, it is showing that nothing is there, then we need to load everything. How do you load? We'll see. How do you load? That means what is ML? ML list avail. ML avail. ML avail basically I pipe it to the more, then you can see these are the available on the system. That means somebody uses compilers, somebody uses math kernel libraries, somebody uses MPI, somebody uses Harvard, somebody uses PyTorch, somebody uses Harvard TensorFlow, somebody uses Python GPU, somebody uses TensorFlow GPU, Xeon GPU, all are available. So all will get listing only. So now what we do, we need to load the MPI is the library. Okay, how to load the MPI library, we'll see actually. So ML load compiler, open MPI. We'll see carefully which version is there, open MPI. Open MPI 5.0.6, 5.5. OpenMPI / 5.0.6. Okay. Are you able to see now? You are
Yes,
able
sir.
to.
Yes, sir. Yes, sir.
What is this command means? You load the MPI library on the system. Similarly, if you want to load the TensorFlow, you have to say ML load. Okay. Similarly, if you want to load the PyTorch, we have to say ML PyTorch. That means you can write the application using MPI library under HPC. Same application you can write using Hadoop MapReduce, Java or Python or Spark Python. So all programs can coexist together, and Slum takes care of scheduling all the things. So now I have done this one. I am now compiling simple program, one for easy for understanding, MPACC hello world.c. So it gives error MPA. MPA, let me just clear the screen. MPACC, MPI it's compiled. That means it is the file /a binary. It is the binary 64-bit everything. So remember always, here the binary is 64-bit. When I start using deep learning, machine learning for the distributed training or distributed inference, then I use a 32-bit, 16-bit, 8-bit also will be there. So we need to be very, very careful. Okay. So now I run one simple code, MPA run, that is what running a program, MPA run -np 12./a.out. So it has run the job on 12 processes, and it has given some rank, everything. You are running a job on 12 processes, and then it launches the 12 processes. One binary is basically rank of each processes varies from 0 to 11. Same job now. Here you are doing compilation execution. Now I will do on the Slum also. How does it really handle Slum? Actually, we should know actually. Okay. So let me see. Now I remove this RM a.out. Okay. Now we have the one. We also use the make files here to compile and execute also. These are the another make file where I have the one master file and one slave file. Let me run the some scheduler job so that you will understand actually. So here, if you go to the hello world, this is a directory. There is a first submit hello.slum is there. Submit hello.slum. Let us see what is it. SBatch, the SBatch is a job name, MPI hello world. And number of nodes, we only ask 2 nodes, but when you really run in the actual real time, when you hire the computing system, you run on 1,000, 10,000 nodes. Nodes is 2. Number of nodes is 2. Number of tasks, that means if each node may have 1 processes or 2 processes, each node may have many cores, each node may have the GPUs also. All things we need to specify. Number of tasks per node is 1, we specified. Maximum time we are given 0.5 seconds, and output is hello output.text, and any error hello error.text actually. And partition standard, that means here partition standard means there are 2 kind of partition which you can talk about. If you have a, for example, we have a 1024 core single address space system is there. In that 64 sockets are there. Every socket is having a we couple 4 sockets as 8 sockets as a 1 partition, another 8 sockets as a 1 partition, and remaining as another big partition. 3 partitions. Each partition is 8 socket means of each socket is having 32 cores. Like this, we have this system. In future, all this come under the chiplet. Every chiplet will have 16 servers. Every server has got 64 cores. Every server has got 8 GPUs. That is how the computing will be more and more in the future actually. So now what you really see is that you can specify all your things as per your requirement of the application. And this also depends upon the performance and cost also. So we need to be very, very careful in declaration of the job name, nodes, output, partition, and maximum runtime, number of processes and everything actually. So now I will here we have already loaded a module load and module load MPA we have done actually, and we have to run MPA and hello world actually. So let us see how do we run actually. Submitted. So how to run the jobs is basically we have to process through S batch actually. S batch, submit. So this is what you are processing. When you really have the Azure Cyclic Cloud with Slum, no changes will happen. For you, it is very transparent because Slum is an open source software, and definitely because of the open source software running on 90% of the HPC systems runs the Slum actually. And each system is today the top 500 supercomputers. If you see the top 500 supercomputers, they run solution of matrix equations AX is equal to B, LINPACK. They're using LU factorization algorithm. And every 6 months, they put the top 500 supercomputers in the list at top500.org. The present system is having more than 5 lakh, 10 lakh cores actually. That means you can able to run 5 lakh processes, MPA processes, 10 lakh MPA processes. All these things have been done by Slum only actually. Many applications, they use the Slum as a load scheduling and job management software. So that means PBS Pro, LSF, Contour, all the schedulers slowly will have a different kind of role, but Slum is going to become very standard. Let us see how do we run also. We are running the same Hello World. In the Hello World, processes with rank 1 sends a message to process rank 0. Let us see. So we are running. Submitted job to 9446. So output has come hello output.txt. Now normally you can see SQ, no? So it tells about the what are the jobs are there, how many are running. We have taken purposefully this system for this today's session. That's why we are dedicatedly running jobs actually. So now when we run this program, we get the output. Let us see what is the output it gives actually. Output says that the system name is called Paramrudra, and then job ID, task ID, account code, job ID number, job name is Hello World, and number of GPUs here 42, 43 GPU have been allocated, but we are not running on the GPU. 2 GPUs 42, 43 allocated also, we are not running. Job user VC Virao, myself, and user ID is 57004. Job partition standard, task PID, and where the directory also there, I put cache, FTP demo, and hello world, and slum rings. That means what here? That the job is run actually on the cluster and it has given the output also. Now same job I run on 16 processes and let us see actually. You're able to see now? Is it clear?
Yes, sir.
We can specify here 16. 16 jobs, 16 processes. One sec. So now basically, since the schedule is a large cluster which we have, each node is having 48 cores. Then we try to run on 4 and C actually, because we already booked only 2, and if we require more, then we need to ask. We need to clean it also. So I'm reviewing. We can use the cleaning option also. So now I'm S batch. So now the job is run on the 4 also. Now question is that we have got now allocation of 42, 44, 43, 42, 43, 44, 47. Now, if your application is completely GPU enabled, and now let us see what is application written also here so that you get understanding of the application also. It is a simple program we have written like this actually. MPA COM size, that is size of the number of processes, COM rank, rank of every processes, processor name, and then print hello world actually. So this is what we have done in this today code. Now, what we do is that we also, so what we need to understand is that this all the Slum scheduler, what we have seen, it takes care of everything, whether it is a high throughput computing or high performance computing. How do you really define all the things is very, very important. And in fact, when it gives in the output, it also gives the complete details about the system and what is asking and what is providing, everything is available. Same thing also, that means in today, Yarn scheduler, which is there in the high throughput computing, Hadoop, MapReduce and Spark, and then high performance computing, Slum scheduler, both are getting integrated. Next time next session, I will run the Hadoop codes also and really demonstrate how they are running also. So today we have learned a little bit about the, an idea about the Slum scheduler. Then we talk about the more things. Then I also run other codes also so that you get idea a little bit actually. Now this is another code where multiple processes can be launched. That means there is a master processes, just like in the Hadoop MapReduce high throughput computing and Hadoop MapReduce architecture, Hadoop architecture, you have the master and slave, you have the name node, data node, you have job tracker, task tracker, you have. Similarly, here master slave architecture, we can write a master program and a slave program. Master program runs on a powerful head node with more memory. Slave program runs on a small nodes with less memory. Then how do we integrate all the things? Master node will have the different kind of problem. Slave will have different kind of problem. Both can be compiled together and integrated to then run it actually. Whereas how we can do these things also important, we need to see actually. So for example, this is what the master.c master program. This master program basically this is our MPA program. Every master is basically master is a process with rank 0. Master receives a packet from process with rank 1, process with rank 2, process with rank 3, process with rank 4. So that receiving we put MPA receive, and then we are able to close the MPA initialization, MPA size, MPA rank, and MPA finalization. And MPA receive is the one command where you are receiving from everybody. Normally in the actual HPC application, there is a broadcast collective communication, scatter collective communication, gather collective communication, and then all to all communication, all things happens actually. Similarly, in the case of high throughput computing, Hadoop MapReduce, mapper task, reducer task, sorting and shuffling, all the things, communication will be more important. That will be internally handled by the MapReduce library. Here, what you see, for only one library called MPA receive, we put remaining all standard MPA init, MPA com rank, MPA com size, and MPA finalize. Now this is a master program. Now we go to the slave program also. Now slave program, if you see, slave program also MPA init, MPA com size, MPA com rank. If my rank is not 0, that means if I am ranked with 1, I am sending to rank 0. If I am ranked with 2, I am sending to rank 0. If I am ranked with 3, I am sending to 0. That is send buffer, send count, destination, MPA com world destination. Exactly same as post office. Post office will do sender will write a receiver address, source and destination. Similarly, receiver receive it. So that's what here. When rank is 1, sending a message. When rank is 2, sending a message. If you have 4 processes, process with rank 0 receives from 3 persons actually. So this is what the other program. So now both the programs are existing. That means master only distributes the work, slave only does the work. Where to schedule, where to run the slave program, where to run the master program, that you can give direction to the Slum, or you can write your leave it to the Slum to handle actually. So here normally in these programs we use either make file. This is how the make file is written here. All these make files we write and compile and execute the code and keep it available. Then you run through the scheduler actually. Okay. Otherwise that you can run direct this program on the system with specialized command and scripting files actually. And that's what one scripting file we are able to see here, npmd. So now this is how the script file we write. That is what one slave program, you compile and create a binary. Master program, compile and create a binary. Then you run both the things. Not through scheduler, directly you can run. Earlier we have run through scheduler. We have run another example through the without scheduler. Now another program I am running without scheduler, where I will use the different kind of binary, different kind of processes. So now let us see. Here in this program, I am running on 5 processes. I mentioned here 5 processes here. This what master runs on 1 processes, and then the slave runs on the 4 processes. That's how we have configured this one actually. So we will simply run the script file sh run.sh, sh mpmd run.sh. So this is a script file we are running actually. So execution is completed, and first we have to make -f, make file clean, will do cleaning, all the binaries removed. Then we execution is completed. So we now we can able to see the results also. Means we have certain things we need to see carefully. All the parts are properly defined or not here actually. We can see which MPI, CC, MPI path is there or not. So another code is that we have the one matrix multiplication code. Where is that matrix mat mult? More readme. So we have to type. This also we are submit through the slum MPICC -o matrix mult. So we have now compiled the matrix multiplication. Let us see ls file is a file matrix mult. It's a binary executor. Now we want to run a matrix multiplication using scheduler. So what is the advantage is that if you really install scheduler and configure on your own single node, single laptop with Ubuntu OS, or if you make the Hadoop cluster and integrate with the scheduler Slum, then Slum can be run everywhere. Either you can run for the high throughput computing or basically or high performance computing. So now this is where this is how the 95% of the application now, one is data intensive, some applications, big data 5 years ago. Now all the applications which are data intensive, they need compute also. When they need compute, they need more GPUs. That means you require a scheduler which can handle the high throughput computing workloads and high performance computing workload. That is where Cyclic Cloud with the Vega platform and then HPC has been integrated. So now we run this code with the this one, submit SQL. as batch. So now I'm running on the matrix multiplication code on the slum. I'm using S batch is the standard command. Job is submitted is 9498. So job is going on and output has come. So it says that number of tasks are 2, compute node is 1, and it says the NPA matrix mult, it uses the 2 processes 42, 43, and output matrix has been printed actually. So for ease of understanding, we have run 2 programs on using Scrum and 2 programs and directly we have run. Like this, we can able to compile and run the programs also. Normally, there are many ways are there actually, which we can do it actually. Okay. I will also try with the one GPU system. Maybe it may be a little bit slow, then we will see whether how we can do it actually. Desktop.
No, sir, you are not audible. Sir, you are not audible. Your mic.
Now okay, no?
Yes, sir. Yes, sir. Yes, sir. You are audible.
I'm trying my best to log in onto GPU node and try to see whether I can able to demonstrate or not how the GPUs also. Are you able to see something?
No, sir.
Okay. Interesting. You're able to see?
Yes, sir. Yes, sir. Now we can see Linux. Ubuntu. Yes.
Terminal here. Open terminal. See, whenever we log in onto the big servers, it automatically takes care of all the environment is set or not actually. Okay. Can we increase the screen a little bit now? You're able to see now?
Yes, sir.
So now what we do, we log in onto one of the system here, and then we'll see how many cores are there as usual. And if you see it's more than 64 cores are there, this is a NVIDIA N40 GPU. And then we type NVIDIA SMI. That is 2 GPUs are there, both are L40 GPUs. You can able to see now text.
Yes, sir. We are able to see.
So now what we do, this GPUs also we can put into the scheduler where number of GPUs, number of nodes we need to declare. When we declare everything, automatically it takes actually, okay. Whereas in the case of high throughput computing, Hadoop MapReduce, when we demonstrate something, maybe next session, we'll understand different kind of way of writing codes actually, okay. So now let us see. Now I will go to the some of the simple GPU test. I will go to the some codes actually. I go to the one makefile. In the makefile, I use the GPU option. I remove some unwanted comments, everything. So that means we have the so as usual, make is a utility tool we use, make clean. So we have done everything. Then we say make. So it is giving some warning messages which we can ignore time being, but it's very necessary for us to address the all warning messages. The compiler maybe after 2-3 versions, warning messages become error messages also. So now I say run is the executable 64-bit. Now I have compiled the Coda device query. That is what the Coda device query. These are the program is the device query. And when we see the makefile, makefile is mentioned about the compile the Coda device query. This Coda device query, this can be plugged with our Slum and run it, but Slum today we ask only compute nodes, but not on the GPUs. So that means we got only compute node. That's we are able to run the jobs using Slum scheduler using a CPU. And when we want GPU means we also have to ask actually. Okay. So now I am running another system with NVIDIA N40. Let's see, /run. So it is run now. Let us see NVIDIA. Now I will store this output file. Then you can see again /run greater than and output. So let us see what is output. VA output. So output, there are two Coda devices are there. The NVIDIA L40, which is the NVIDIA L40S is 4 years old. Now today, CDAC, we have the NVIDIA H200 and we also got NVIDIA RTX 5090. All will be merged with our scheduler actually. So we have Param Siddhi, which is 120, more than 240, 256 nodes. Each node is having 4 GPU. Each GPU is having 64 GB memory. And another one is Param Airavat. That also has got more than at least 1,000 GPUs and more than 10,000 cores kind of thing. All those are running on the Slum scheduler only. Okay, both are integrated together differently. Now the internally we run our cloud for many things, but when we really launch commercial cloud, it has to be service oriented. That is work is in progress. Now what you really see is that NVIDIA GPU L40S, there is shared memory, global memory, and number of streaming multiprocessors, number of scalar processors, and total shared memory for threading block, number of threads per each block, and number of dimension of the grid, dimension of the blocks, and streaming processor, global memory, shared memory, constant memory, texture memory, and number of VARPs. VARP is VARP is scheduling on the NVIDIA GPU. This is the VARP. 32 threads are formed as a one VARP, and each thread is a unit of computation. And you have the more than 142 multiprocessor SMs are there. That's a Coda device 0. Now you also have the Coda device 1 also, same thing you have. Coda device 1 also. Coda device 1. So what does that mean basically? You have the two GPU devices here on 160 with 64 cores on the CPU, and you can launch many threads on the CPU, and every thread is binded to the either one GPU or two GPU. And now all these GPUs earlier 4 years ago they are doing 64-bit computation. When we do the 95% of the AI applications, including deep learning, machine learning, all AI applications require matrix into matrix multiplication. What does it mean? They perform a group sets of matrix multiplication. That means if you say 64 sets, each set is a matrix into matrix multiplication of 20 by 20 or 30 by 30 in the case of neural networks and everything. Now you are performing 64 such sets in matrix into matrix multiplication. And when they do in training, it is 64-bit. When you do the inference, it will be 16-bit. That means 64-bit, if you require 8 GB memory, if you use 2 lakh threads, for 16-bit, you require 2 GB. Your memory will reduce by 1/4, but number of threads will be increased by 4 times more. So that means 99% of the programs are running on the GPU. That means all our schedulers, including our scheduler, what we integrate with the cloud, it runs on GPUs only. So that means what? Most of the schedulers from and then Azure cloud and all things, they have constrained that how many GPUs require, how many are available. And you can also ask GPU 80 GB, 160 GB memory so that your applications can run much, much faster actually. So what I covered today is Slum scheduler running on the Rudra cluster, and another NVIDIA GPU N40 also how it is run. We are run 2-3 programs on the NVIDIA GPUs L40 as well as the matrix multiplication using Slum scheduler submission, and we also run some programs without Slum scheduler also. So this is what we have done. Now we'll get back to the our presentation and discuss clearly about what we discussed actually. Okay. So before that, I will just log out from my session. Any questions are there about the programs, everything so far? Is there any questions?
Participants, if you are having any queries, you can write up in chat box. We will convey the message.
We did not discuss codes running using Python GPU. MPI Python means if you really see Hadoop, MapReduce, high throughput computing, Hadoop, Python, one programming stack, Spark, Python, another programming stack, Spark, Python with GPU, another programming stack, Hadoop, Python, GPU, another programming stack. Now for the AI, we have the PyTorch GPU, PyTorch MPI enabled, TensorFlow, all environment is available on the system. That way, when you run the programs on the Slum, first you load it, compile it, and then submit to this scheduler. That's what we have to do. Now before we quickly close up our today's talk, now we go back to the Azure cloud actually. Now what we have gone through is the Slum scheduler, some examples. We have also gone through the Rudra cluster, HPC node, where the 48 cores are there. We also gone through the another compute node where 2 NVIDIA GPUs with 48. We also have the AMD GPU cluster. We also have the Xilinx FPGA cluster at CDAC Pune. What we need is that if you really ask and block some time on this cluster, we have to make a request much early because many jobs are in the queue and it requires some time to launch your job also. It's a lot of heavy workload is there on the systems actually. Okay. Now come back. We discuss about the now what are the things, how do we really set up the Azure Cycle Cloud with the Weka that platform? One is download the Azure Cycle Cloud Weka integration template, configure network parameters for the DPDK, deploy the customization module, configure the Weka blade, and test the integration. That's what we have to do. When you test the integration, we need to see all the workloads which application requires. We need to capture and write more scripts and submit it actually. So this is what the Weka platform which we discussed. Now we'll go to the little bit next step. So now we all discussed about the Slum and we give more details and close it actually. Slum, many of the oral, now I skipped some basic. Slum supports complex job scheduling, optimization for network topology, fair share, advanced reservation, preemptive gang scheduling, and more. The primary function of Slum is to allocate resources within the cluster to users. When you say within the cluster, Slum has been designed for high performance computing. Now Slum is basically moving on to the high throughput computing also. That means the Azure cloud can really provide everything. It will also allow you to integrate your third party schedulers, but it has to work on the extra LDAP and directories to see that everything. That means protocols and services has to match whenever we integrate with the third party schedulers actually. Now what you see is that the GPU usage, GPU cost of GPU, number of hours of GPU, number of hours of CPU usage, everything come under the cost actually. That is also another important. Okay. You can also manage the nodes, you can also manage the sockets, you can also do the hyper-threading, everything you can ask in the Slum resource management actually. So this is how the Slum look like actually. You have the socket, you have the memory, you have the generic resources such as GPUs, you have interconnect switch, software licenses, and hyperthreads, and you have the cache on the board also. All the things are there actually in the Slum cyclic code version. But all the resources are managed by the Slum, whereas the cyclic code takes care of the your security, policies, administration, and availability. All things it will do. So both are integrated in a single framework now. Slum and cloud development. Slum clusters running in cyclic code revision 7.5. Google Cloud Platform also runs on the AWS. So what I'm saying is that Slum runs on the almost all the clouds also now. It's more popular. It can be improved much better. It can be fine-tuned also. It's being open source software. We can learn many things actually. Okay. So I recommend many of the students and faculty members, they can improve the load scheduling job management software where they can use the Slum actually. Okay. Now actually, now I told you that there are many systems in the cloud. Some systems may have 5 and 12 cores. Some systems have 1024 cores where 32 sockets. Every socket is having 32 cores, 32 socket, 32 core, and 32 TB memory. Such high-end systems, you can do partitioning the cluster. When you partition, give me 8 socket partition, give me 16 socket partition. All things are possible with the Slum and cycle load. What is the advantage is that if you have 8 socket partition, you can create, if every socket has 64 cores, if you have 8 socket partition, then you have 5 and 12 cores. Because you have 5 and 12 cores, you can launch more than 100, 200 VMs and processes also. That means launching VMs on every socket, number of cores on every socket, all these things you can set through the Slum scheduler only. So it makes very easy for the user to estimate the workload and estimate the resources required and run the job actually. So this is what the very good cluster management and job scheduling software. It can be many fine-tuned also for the many applications. Okay, here the Slum can be configured to topology aware. Topology aware means what? Today, all the top 500 supercomputers, if you really see, the first top 500 supercomputer may have more than 10 lakh, 20 lakh cores. If you have 10 lakh cores, core processor machine, if one user wants 1000 cores, another user wants 2000 cores, then what is the which 1000 cores we need to choose, how the 1000 cores are really connected, what is the latency, what is the all-to-all communication, what is the round-trip communication bandwidth, how they are connected. All the compute nodes are connected using the mesh topology, using star topology, using torus topology. Then which topology they are connected, what is user wants, what we require. All these things are topology guide also there actually. So that means you can able to specify all your requirements in the Slum, a cluster management job scheduling software that takes care of everything available. So now the question is that what are the available resources in the cluster? What user wants? Somebody wants flash array of SSDs. Somebody wants data movers from the flash array of SSD to main memory. Somebody wants main memory data to come from the all these things you can write scripts that also you can configure in your cluster actually. So that means what? you can define your own scheduling policies on the slum based on your scheduling policies. That is, scheduling policies means how many GPUs you want, what kind of intermediate memory, flash array, SSD is required, and what is the storage required. All these things also you can specify in your slum as a service provider, and you can able to meet the demands of the user actually. Now, another important is how the slum is monitor the jobs. What is the report status? We have seen what is there in the queue. All the things also we can able to get in the slum actually. Now, who is basically resource management? Oracle Marketplace provides high performance computing RDMA cluster network image. RDMA cluster network developed by the Oracle HPC group. That is also with the slum actually. Okay. Similarly, Open MPA, which we use, that is also equipped with the tools to test MPA. So with all the things, Scrum is going, then Microsoft Cycle Cloud is also growing. So this is one thing which we need to understand actually. What is the advantage of this Slum running in the cloud environment? And then how we can handle the different kind of clusters. So all these things are come under the high performance computing. Whereas high throughput computing is slightly different, where we use the Hadoop distributed file system and MapReduce framework, name node and task node, data node, and then job tracker, task tracker. So we need to get idea about both the things to when we use the load scheduling job management software in the cloud environment actually. Now, the command what we use sbatch is a one command used for the submitting job, and salloc, that is allocating resources for the job. Srun, submit a job with MPA jobs. Cancel, you can also cancel a job. And sinfo, status of number of partition nodes, everything. Queue, whether a job is in the queue or not. How the all this information about the system is also useful for the user actually. Now we have run for today's job on using a following script sbatch, and your script goes actually. Okay. So what I covered today. So what is important now? Cyclic Cloud open source cloud native HPC. Slum with Cyclic Cloud combines the best of open source and cloud native HPC. And efficient scaling. Now with this, you can add high throughput computing. That's where Hadoop MapReduce, HDFS, everything will come also actually. That means Cyclic Cloud is a Azure orchestration platform for HPC. Why HPC is becoming more popular? Because today, almost all 95% of the application run on distributed deep learning, distributed inference. All the distributed AI applications uses 1000 node cluster, 2000 node cluster. Every cluster is having 8 node NVIDIA GPU or AMD GPU. With all 8 GPUs connected with NVIDIA link, and each GPU is having 80 GB, 160 GB memory. So that way what happened, high performance computing is totally necessary for the present era of computing actually. So that is the reason Cyclic Cloud Azure's orchestration platform for HPC with Slum, with Weka, it's very, very good open source cloud native HPC. So this one can really start these things actually. So this is how the Slum and Cyclic Cloud core capabilities were very, very important. We need to understand what are the core capabilities which they have and what kind of capabilities required from application also. This is also very, very important. And cluster design, how the cluster is designed, that means the cluster consists of 1000 nodes. You have a powerful head node, remaining nodes are the compute nodes, and you have the shared storage, you have the InfiniBand kind of networks. Every node have the CPU, GPU, and they have different kind of socket partitioning, different kind of workloads. All things we can integrate in the Cyclic Cloud and Slum actually. When you integrate all the things, seamlessly you can solve many applications on the Slum and Cyclic Cloud actually. So the good amount of work has to be done by the service provider in the writing scripts and checking the scheduling jobs, as well as the how do you choose the best nodes, for the application requirement using topology-aware algorithm, and you require a lot of tools to do these things actually. So last slide I'm going to conclude is that, so job submission, monitoring and scaling, all these things are basically done using the Slum with the Cyclic Cloud for only HPC. Now in future, HPC and high throughput computing both can be integrated so that optimize the cost and optimize the throughput actually. So as today what I have covered in the overall from the evening session 4 o'clock onwards, we gave some overview about the scheduler in high performance computing, schedulers in the high throughput computing. Then we also discuss about the how the Azure Cyclic Cloud is positioning their own work with Slum HPC scheduler, and Slum is an open source software which is widely used in all supercomputing centers. We have also run 2-3 examples using Slum where the S batch and queue and job specification we understood actually, and we also run some jobs using the without Slum also. And we also logged on to the on GPU system and then run the GPU device query, everything. In a given time frame, it's difficult to go through the each and every script, each and every program. But what we have learned today is that high performance computing and Slum, the Slum and high performance computing and Azure Cyclic Cloud all are basically going to drive many applications in future. It's being an open source software, we can invest more time and learn about these things also. So we are not discussed much about the high throughput computing, Hadoop, MapReduce, and Spark Python will take up next one. With this, I'm now actually open for some questions for my session.
Participants, any queries, you can put up in chat box. So, sir, I think there are no queries, sir.
Thank you very much.
So at last, like I would like to thank you, sir, for giving such a wonderful practical insights on how Slums works and showing CDEX servers and high cloud computing systems. So thank you again, sir, and we will be happy to get more insightful information from you in upcoming sessions. Thank you, sir.
Thank you all.
So dear participants, we will meet again tomorrow at 9:30 a.m.